Hi everyone, I am Matt with Cognacode and just want to show you a quick trick that we use in a lot of our engineering that has made a really big impact and saved us a lot of money, made our actual infrastructure more efficient. That is pretty easy to do, and I think a lot of you guys can benefit from it also. So most of you who are familiar with our company probably think of the machine learning and a lot of the algorithms and productionization of algorithms that we do. But a core component of our work is actually app development and integrating those apps with our machine learning. And as part of that, it's really important to us that our apps are super, super fast. They work well in any infrastructure. We want them to be cloud agnostic. And one of the big challenges that you'll come up with when you're building a production app, particularly talking about web apps that are written in JavaScript or TypeScript, is your final build. If you're using a Docker container or just some way of shipping your build, then it's going to be really big. A lot of times it'll be 2, maybe even 3 gigabytes, which is huge to ship a production app. So I want to show you something that we do where we use a custom app server. So we've built our own app server. We essentially override what a node server or even a bun server might be doing, and then we write our own thing, compile it into binary, and then ship that. And you're gonna see a drastic improvement in the size of your production build, as well as in the efficiency, and you can also use it for massively improving some of your production performance, especially if you're using it for your API as well. Okay, so let's jump over into an IDE. So here's 2 Docker files. So on the right, you'll see a fairly standard Docker file for this here is a Next.js app. We like Next a lot. It's great for building out the UI. And generally what you'll do to keep your image small and efficient is you'll build it in one layer, and then you will create the image to actually run it in the next, and only copy over the elements that you need. Then you start it up, and you can throw this on Google Cloud, AWS, whichever cloud provider you prefer, and just enter this in, map it to a port, and you're good. The way we are doing it, if you look at this Docker image, is you'll see we have still a build step where we pull in Node, we build our app, and then we have a second step where we build our server. So we use Rust. For anything high performance, we'll generally use C++ or Rust, but we've had a strong preference for Rust in the last couple of years. Really, really good outcomes. We're more effective in it, and in our benchmarking, we're getting equivalent or even better performance than some of what we would build in C++ before. So now we build a server, and then here we have this basic. So Alpine is just a very basic Linux container, and we install some requirements. You probably actually won't need this in production. I need it because there's a translation between the ARM architecture on my MacBook that I'm using now and the x86 architecture that we're going to be using in the container. So after all of that, we can just execute this binary and start the server. Before I started this, I kicked off the build. Here's a quick build script I have. Basically, we're building the normal Docker image, then we build the optimized one with the custom server, then we start both of them up normally, and we just log out how long the build time was for each of those. And you can see they're fairly equivalent. So the optimized one is 1 second faster. That doesn't really make that much of a difference. But here is where the magic is going to happen. When you come into images, and you can see both of those. So we have a standard Next image. So it's about 2 gigabytes. That's fairly standard for fairly standard for a JavaScript application. But if you go into ours, which is based on the binary, then you get 33 megabytes. Like that's so much smaller. That's a fraction of a percent of the size. So you don't need to pay for all that extra server cost if you have multi-tenancy, or if you have some redundancy, you have some like distributed systems. Well, now your whole infrastructure is going to be so much smaller and more efficient. You couple that with the idea that you can ship it faster, right? I mean, if you need to move stuff around the web, get it into different clouds, you can do that much faster with a tiny little build. And also, any APIs or whatever that's built into it, you can leverage concurrency, which is much harder to do in Node efficiently, and it will just, in general, compute a little bit faster. So we have the two images that you can see here, and I also started both of these containers, as you can see. One is running on port 3000 and one is on 3001. So now if I jump here, you can see that both of these are running, and we can come here to localhost 3000. Let's go to the standard next one first. And we're currently using our website and some of our infrastructure template for this demo. It's slimmed down a little bit to make it simpler to show off in a quick video. But now we come here, you can see this is a fully functional website, has all of this stuff. But what I want to do is come here to this approach tab, because it's got some images, and we have intentionally shipped not optimized images. So these are big. These are multiple megabyte images, which of course in production we will use optimized formats. But I want to show you that the next server is not going to be a benefit. There's no loss to doing it this way. There really is only gain. So if I now take this and we jump over here and we go to 3001, boom. Now you can see that we are in the new optimized build. And of course we can click around, animations are starting up, things are shipping quickly. But let's go back to here where we got some images, and yeah, so we can see that this is working well on both, right? We have them running concurrently. So how are we doing this? Well, the whole idea is that when you build out your UI in Next, you can essentially export everything into your static assets that then become rendered either on the server or in the or on the front end. So what we're doing is we can jump into our actual project of how we built this, and can close this for now. So here we just start up a basic server that has one route for the actual index. So this is when somebody first lands on the app. We ship them the pre-rendered HTML landing page so that the time to load is really fast and they don't have to wait for anything. And for all other paths, we send them to this dynamic route. And then finally, we have this state. Now, the state is going to be available to any of these routes, but this is actually a in-memory representation of the file system that we've created. So we have held in compressed binary in the memory of the system. We have all of the HTML, the images, the JavaScript, whatever the front end needs to be shipped. We have that all held in a tree structure in memory. And this is shared immutable memory. So anytime that it needs to be accessed, there's never a step of take these bytes from this memory slot and move them to this memory slot, which is slow. What we're doing instead is we're using atomic reference counts, which for people who haven't worked with some of the lower level code, that means that we basically just have a place to go find where this actually lives. So we have a pointer, and then we have a like metadata about that pointer, specifically how many pieces of the program are reading it. And what that does is it lets us be so much faster and more efficient. So this will scale much better than your base Next.js app would, right? If you blow up overnight, or get DDoSed or something, this is gonna help really counteract that scaling. All right. So realize I'm taking a bit here, but to walk through what we're actually doing here. So standard tree structure, where we build this tree when the app first comes up, and then it becomes that shared immutable memory I was talking about. So we have files, which we list all of the files in that static output directory. Then we have two structures. One is a basic, hash map, like a lookup, or a dictionary if you guys work in Python. Basically, we have a key, which is every file path, right? So we can say that at let's say home/html.index, here is the binary, the actual bytes that we ship to the front end. We also build out a standard tree structure. So we have a hierarchy of trees that we can recursively search to find any given file by its nested directory, as well as dynamic routes. So if you guys are familiar with file-based routing systems, then you will have something where you can have a variable that is coming actually from the URL string, or you can say every path after this becomes a variable that gets passed to the software. We represent those with these dyn and dyn all keywords. That is just by a convention that we've created. It's not actually meaning anything here. And then we have a standard node and recursive search structure. Okay. So as you can see here, what we do is for every file that is required by the app, we loop over, we infer what type it is. So is it HTML? Is it a directory? Is it, a video? Whatever it might be. Then we read it in. So here you can see we just have these unsigned 8-bit integers and a list of them. For anyone who's into the engineering, you're going to immediately understand that is bytes, or a binary representation of data. For anyone else, basically this is just a representation of all those ones and zeros that we need to build out, like what an HTML file is, what an image file is, any of that. Then we come down here and we optimize the backend by compressing it using gzip, common compression algorithm, and we store that then inside of the tree. We build out all of these nodes, so we walk the file path to get everything that is required in the directory, and we then, standard building out a tree structure, and we return back the tree and the file lookup. So when somebody actually makes a request, if it's the index, we just grab the index and return back that file, right? We don't need to wait for anything else. Most important thing is that page load, so we can ship that quickly. Then finally, or the next step here is, if it is not, then we will serve an asset. So we'll have the state, which remember is the memory representation of the file system, as well as that tree that we can search. And then we will have the actual path of what somebody is requesting. We will go through, find all of that, serve it to the front end, and then finally we will have something that's going to the front end, it's optimized, and at that point, it now behaves exactly like a normal app would, only much smaller and more efficient. So thank you at this point for watching this, and please reach out if there's any like questions or things that we can help with. Honestly, I get excited about a lot of the app development stuff and the engineering pieces of the work that we do. So love talking about this, and please, please reach out. All right, thanks a lot, and I will hear from you later. Bye.